All right. Well, first we will start with homeostasis. Okay. So, homeostasis is when you are trying to keep something within a normal or safe range. An example of homeostasis would be temperature. So, this would be temperature and this is time. So over time, the temperature can vary a little bit. And this is the normal range that it is usually in. And this line right here is called the set point. So the set point is pretty much the normal. And with temperature, it's about 98.6. But with, for example, a fever, the set point can go up. So then this line right here becomes the new set point, becomes the new normal. Of course, this is for a short amount of time, so it'll eventually come back to normal, but anything going back towards the set point is called negative feedback. Negative feedback is important for our bodies because we are returning back to that homeostasis. Let's see. Positive feedback is different than negative feedback. An example of positive feedback would be blood clotting. When a wound occurs, the platelets at the injury site release different chemicals that recruit more platelets to help clot. And so that positive feedback will continue to tell the body that they need more platelets and they need to clot. And if this continues on too much, you can have clotting in places that are not desired. Positive feedback is when something is broken, something is not working correctly. And with these feedback loops, there's different things that are associated with it. For example, a stimulus is what signifies that there is need for a change or something that causes the change. For example, let's say this is a hot burner. So that is a stimulus. And then there's a receptor. This receives the signal. And then it goes through a pathway. There's an afferent pathway or efferent pathway. So the afferent pathway takes it to the control center, which is the control center. And then efferent takes it away. So, for example, from the control center. So, the control center is the brain. Then you have what's called an effector. So this is the actual change. So that's the action of moving your hand away from that hot burner. So it goes through an afferent pathway to get to the brain, and then coming from the brain, the efferent pathway tells the body to move the hand. And that is homeostasis. And feedback loops, of course. Now we'll be talking about protein-mediated transport. So there are different types of protein-mediated transport. There is, let's see here. So there are 3 types. There is passive transport. And there's active transport. And there is also, with this passive transport, you've got facilitated diffusion. And simple diffusion. So the facilitated diffusion just needs a little help. So these are bigger things that are trying to go through the membrane. Simple diffusion is like CO2 and O2. It just goes right through the membrane very easily. So in the membrane, you have hydrophilic heads and hydrophobic tails. And that is what makes things harder to get through the membrane. And permeability is the ability to go through the membrane. So there are different channels that are used to help things get through the membrane. And one of these channels is called a voltage-gated channel. So there is an activation gate, which is this, and then an inactivation gate. So the activation gate obviously activates that the gate will open. So the gate will open, and then things can go through, and it's very specific on what it'll let through. And then the inactivation gate deactivates the gate and closes it pretty shortly after it has opened. Another gated channel is called the ligand gated channel. So ligand gated channel is when something attaches onto the gate like a certain chemical, there's a receptor site that allows the gate to be opened. There's also mechanically gated channels. These are opened by force, whether it be like pressure or touching something, that will cause these channels to be opened. And then you also have sodium leak channels, which is a channel that is used for consistent movement of potassium across the cell. There are also, with passive transport, there are carrier proteins. So these carrier proteins can open when something attaches. So say we have a gate kind of object here. It will need a specific molecule that fits exactly right in there for it to bind. And then once it's bound, it'll open up it'll have a new spot for a different molecule to bind. For example, if we have a molecule that looks like this, it would bind. And let's see. That is everything with passive transport, except that there is a rate of transport through the membrane. Obviously, larger molecules go through slower. And polar molecules will be slow, and non-polar molecules will be able to diffuse through the cell quickly. With this as well, let's see. Oh, saturation. So saturation is when, let's say, you have a certain amount of cells trying to get, a certain amount of molecules trying to get through the membrane. But there's only a certain amount of doors for it to get through. Say you're at the movie theater and there's only 4 exits. There can only be so many people going through those 4 exits at once, no matter how many people you have. So you reach a point where you are unable to keep on letting people through, and then you have a steady line. This is saturation. And let's see. With saturation, there's also specificity. So with specificity, that is when the transporters are very specific in what they let through into the cell. Like they have the VIP pass, the backstage passes. Now on to active transport. There is primary active transport and secondary active transport. So primary active transport is kind of similar to the protein, the carrier proteins, has different binding sites, but primary active transport uses ATP. As well as secondary. That's the thing with active transport, is that it requires ATP. Passive transport does not require ATP. Okay. So primary active transport moves things against their gradient. An example is the sodium potassium pump. There are different sites for the sodium to bind to as well as the potassium, and when they're bound, it allows that part to open. And then secondary active transport, there are two types. There is a symport, which has both moving together in the same direction, and then you have an antiport, which moves them in opposite directions. Oh, like that. That, I think, is all for the protein-mediated transport. Now, finally, we will talk about osmosis. So, for osmosis, there are a couple different things that we need to know. Osmolarity is the amount of moles per liter. It's moles of particles. So osmolarity is moles of particles per liter. And osmolarity is used to measure particles and liquids, whereas molarity is used to measure atomic mass units of a certain element in chemistry. Tonicity is pretty much the firmness of the cell when it's placed in a solution. So if a cell was put inside a solution. So as well as with osmosis, usually we are measuring the cell and the solution independently of each other. But with tonicity, we are measuring them both together. So just as a unit of measurement, we use about 300 milliosmoles for a solution. And then there's also 300 milliosmoles in a cell. So if we have dextrose, 5%, this will make, well, this is for osmolarity. So if we add 5% dextrose to the solution, we will be adding 300 milliosmoles. And then this will make the solution hyperosmotic. So, because it'll have 600 milliosmoles, whereas the cell will still only have 300. But for tonicity, we have the cell and the solution together, and this will become isotonic. Because this extra 300 will dissolve into the cell. So we will be back to normal, which is an isotonic environment. When a cell is swelling in an environment, say there's more particles inside the cell and less on the outside, that is a hypotonic environment. And then if there is a cell that has less on the inside of the cell, this becomes a hypertonic environment or solution. So with solutions, let's say we have sodium chloride. Which is 0.9. we would have Hmm. 600 milliosmoles in the solution. So 600 milliosmoles but this is the exact same solution. So this is an isotonic. Isoosmotic solution. But when put them together, this sodium chloride or saline is non-permeable. So it's going to want to stay on the outside of the cell. So you're going to have more water on the outside of the cell. And the water likes to party with all the other particles. So it's going to leave the cell, making it a hypertonic. A hypertonic solution, yes, because it will make the cell shrink. And so it's important to remember that dextrose dissolves in the cell. It gets metabolized, and then saline is non-permeable, but it's the exact same solution as what is on the outside of the cell. So tonicity is when we place the cell into a solution and see what happens. And then osmolarity is when we just count the number of particles. And yes, that is osmolarity and tonicity. And I believe that is it. It is possible for a solution to be isoosmotic, but also hypotonic. That is when you have dextrose and saline together. So the dextrose would go into the cell, and you would have more inside the cell, making it hypotonic. But eventually it would get metabolized. But yes, that is everything. Thank you for listening.